Hello everyone. So today we are going to go ahead and work on building our dataset and then the data loader necessary for neural machine translation. I was a little bit on the fence if I wanted to do the dataset stuff first or build the model first, but I decided that if you see what the data looks like, then it's easier to explain the model and you'll kind of have an understanding of why we're making specific decisions when we actually go to build the model in the next video. So today, we are going to build our data set. Now to build a data set, there's a couple of steps that we need to take. So the first one is we actually need data. So let me actually pull up the link here to the data set. This is the WMT translation task. Here we go. It looks like this. We will be working on French to English or English to French translation. So I just downloaded some of this data here, and it should give us everything we need to actually do our French to English translation. I downloaded it to this folder. So I made 4 folders here. We have Common Crawl, Europarl, GigaFrench, and UN Corpus. And inside each of these folders, we have a English and French text file. So this is the raw data that I downloaded. We could have also gone to Huggingface and just grabbed a pre-prepared data set, but I wanted to show how would you go about making your own data set from some raw text files. So we will be using the Huggingface platform, particularly the Huggingface datasets and their tokenizers. We'll be writing our own models and all that sort of stuff, so that'll be us. But for kind of the more logistical things like this, we're going to be leveraging some of the tools that they have because it makes our life a lot simpler. So you're also going to see this for a lot of the videos that we'll be making everything from scratch when it comes to the model, training, that sort of stuff. But when it comes to kind of data set related things, I just love using their platform. There's a lot of helpful functions that you're about to see when we do them. So when it comes to data, there's actually going to be 2 things we need to do. Number 1, we need to build our data set. And number 2, we need to build a tokenizer. So we've talked about this before. A good example of this, again, is the OpenAI tokenizer. So let's kind of take a look at this real quick. I love this. This visual. So we can give it some text like Priam loves hamburgers, right? So this is my text, but neural networks, they don't get text, they get numbers. So we convert them to token IDs. So someone has done or created a tokenizer that converts text to numbers, right? Just like that. So the conversion between them. So we saw this a little bit when we're doing the recurrent neural network stuff for the sequence classification and generation. We need a tokenizer to convert text to numbers. Now, when it comes to English, not really a concern. We can just, we're going to be using the BERT tokenizer today, so there's no problem there. When it comes to French, we could just use a French tokenizer, right? We could just use one, but I thought it'd be fun to make our own tokenizer just so you can see how it works. So again, we'll be leveraging the Hugging Face tokenizers package to do this. If you're particularly curious about how you would build your own tokenizer, there's a great video by Karpathy that I'll link below that you can definitely reference to learn a little bit more about that stuff. So to create a tokenizer, there are a couple of steps we need to do. So we're going to create a function here called train tokenizer, and we're going to give this the path to data root, right? So it's going to be the path to our data, basically that folder with all the folders of data in it. And we're going to define a couple things. So first, our tokenizer is going to be the tokenizer class that we import in, and we want to create a word piece tokenizer. Now the word piece tokenizer is the kind of the tokenizer that a lot of language models like BERT use. The one that a lot of the generative models are using, like Llama, GPT, that sort of stuff, they're using the BPE tokenizer instead. What's the difference? Probably not much for the purposes of what we're trying to do today, but you can imagine all of these things as subword tokenization. So they take words, or they take a corpus and break it down into the most common subwords there are. And so BPE tokenizers seem to do smaller subwords, so it's like maybe smaller chunks of words, where word piece seems to have some larger chunks of words. And you can imagine that the smaller the chunk of words, the less meaning that's in them. Like if we take the word, I don't know, we can take, let's say, Applebee's, right? The restaurant Applebee's. And so Applebee's, if we take Applebee's and chunk into Apple and Bees, both of these words actually mean something on their own, right? So that's fine. But if we take Bees and split it into BE and ES and then Apple into AP and PLE, each of these tokens don't really mean much on their own. So WordPeace seems to have slightly larger tokens from what I can tell, or basically tokens that each of those things represent. So they can probably encode some more actual information about what they mean. So either way, we're going to be going with WordPiece. And for WordPiece Tokenizer, we need to define a couple of extra things, and these are known as our special tokens. So I'm going to create that above here, special tokens dict. And we're going to create, so some of these we've seen, unknown token. So we're going to just call this unc, right? Our unknown token. This is going to be our placeholder whenever we are seeing a token or some text that our tokenizer doesn't include. So we just have a placeholder in case we don't have that information. We have our pad token, right? So we can do that here. Oops, my mistake. So we have our pad token, and we're going to call this pad. We have a, these are the new ones. We're going to have a start token. This is going to indicate the start of a sentence, and we're going to call this BOS, or beginning of speech. And then we have our end token, right? And this is going to be similarly EOS, end of sentence. Sorry, not speech, sentence. Beginning sentence, end of sentence. So start token, end token. And we're going to need these, especially when we write our generative script in the next video, when we actually write the model. So for now, this is these are the special tokens, and you'll see kind of how we use them in a bit. So we have our WordPiece tokenizer, and we need to provide to the WordPiece tokenizer our unc token right here. Unc token is, well, we already said it, so it's going to be unc, right? Just like that. Good. Now to our tokenizer, there's a couple things we need to add. So tokenizer.normalizer first. So normalizers, how do we want to prepare our text before we actually tokenize it, right? And so there's a bunch of methods or things we can do here, but we're going to go simple today. Sequence. So we're going to do a sequence of some transformations. The first one is called NFC. So this has to do with Unicode. Let me copy this right here and paste it right here. So in this Unicode, when you have E with this apostrophe on top, it can be written with this single Unicode character. If you don't know what Unicode is, just look it up. It's pretty simple, but basically every character has some unique Unicode, right? Something that represents it. So E apostrophe can be written as this, or E apostrophe can be written as E plus apostrophe. So this would be a sequence of 2 Unicode characters. And different text files or formats might do this differently. There'll be different formats. So an important first step is to just make everything homogeneous. And NFC is the most generic Unicode normalizer. There's some other methods out there, but I'm honestly not in the know-how of Unicode logistics, so I'm going to leave it there. But as simple as that, we're just going to make sure that our Unicode is kind of all the same for all of the text that we're working on. Next, we're just going to make sure our text is all lowercase because we don't really care about uppercase right now. So we're just going to keep everything lowercase, and that'll be it. Our English tokenizer in the future, that we're just going to use, the BERT tokenizer, is also all lowercase. So it just makes sense. And then we're going to do a tokenizer.pre tokenizer. It's going to be white space, right? So our pre-tokenizer is there something we want to do before we start the tokenization? So like I mentioned, the tokenizer basically looks for the most common subwords in your text to act as your tokens. The obvious place to start is by cutting up our sentences by white space. Like English and French and a lot of languages out there have spaces between words. So white space would make sense here. In other languages, like Japanese, you may not have a white space between your words. I think Japanese doesn't have white space. I don't know enough about other languages to actually say for that for true, but I'm sure there's languages out there that don't have white space between words. So there we go, right? So we can, for the purposes of French, we can split on the white space, so we're good. Next, we need our French file. So actually, this will be easier if we do train tokenizer. And we're going to pass the path to data root is path to data root. And we're going to look at our French files is going to be, let's see here, it's going to be glob.glob. So we're going to be recursively looking inside os.path.join. And we're going to be looking inside path to data root and our ***/star.fr. So what's going on here? Basically, we are pointing to this folder, and this first ** says you can check inside each of these folders. So you can go with the depth of 1, you can look inside a folder. When you go inside, I want *.fr, which is going to give me the file that ends with French, because I only want the French text right now, because I'm creating a tokenizer for French. So we print French files. You should see, looks like I spelled something wrong. Tokenizer. Nope, that's correct. French tokenizer from Tokenizer. Let's see here. Cannot import French tokenizer. Let's see, Python tokenizer. I think I'm just running the wrong file. There we go. Okay. Yep, running the wrong file. I can actually ignore this. This is fine. Okay. So we have all of our files here, right? All the French files. And so we're good to go. So we're going to pass these to our trainer. So now we need to define the trainer. Our trainer is going to be the word piece trainer. And one thing we have to decide ahead of time is what vocab size do we want to use, right? So 3,200 is too small. 32,000 is what I'm going with. I think that's very similar to the BERT tokenizer. You could go more, you could go less. It's kind of experimental for you to try and see what you want. Big language models use large tokenizers, like 100,000 tokens or maybe 200,000 tokens. So they can get very large very quickly. Just do know that the bigger your vocab size, the bigger the embedding matrix in our model will be in the future. So there we go. Now the special tokens, all we want is the special tokens dict and dot values, right? So we're basically just converting, we just want unc pad boss EOS, so we're just getting a list of our tokens there. So there we go, trainer. Now that we have our trainer, we want to go ahead and train it. So we're going to do tokenizer.train. We want to train on the French file. So the tokenizer built in, or the Huggingface Tokenizer is going to train on a list of text files, and we have to give it the information of the trainer. So that's this right here, trainer. And once we're done, we're going to go ahead and tokenizer.save, and we're going to save it in train tokenizer, and I'm going to create a French word piece.json, right? So we're going to save it there. So this is our training function to create our tokenizer. And again, basically before we train the model, we're going to split by whitespace, do all this Unicode and lowercase normalization stuff, and then it will train. And when we actually go to use the tokenizer, we'll see what that looks like in just a bit. So we can go ahead and run tokenizer. So initially it's going to iterate through all of the data and just process it. Now the reason this can actually happen in a reasonable amount of time, it just takes a minute or two, is because in the backend, all of this fun tokenizer stuff is written in super fast Rust. So it saves a ton of compute time when done correctly. So there we go, that's our training script. Now this will produce a tokenizer that we can use. I just wanna make a slightly, basically a wrapper on that tokenizer, because all this tokenizer can do right now is encode and decode, but we need a little bit more functionality out of it. So we're going to just add an extra wrapper on top. That'll just keep going in the background. That's fine. So I'm going to create a class called French Tokenizer, right? And this is going to have an init. We're going to give it the self, the path to the vocab, basically the JSON that we're saving here. We're also going to give it a truncate equals true, like anything that's too long, we want to truncate it. And max length is 512. So that's the maximum length of sentence that we want to have. And so let's go ahead and save some of this stuff. Let's see how you're going. So you can see it is tokenized the words, it's counted up the pairs, and now it's computing up all the merges. And once it's done, right? So it has saved our tokenizer. What this tokenizer looks like is this, right? So we have some of these special tokens, unc, pad, boss, EOS, and then we have all of our tokens, right? So we can see that these are all of the tokens. I notice it starts with small letters, and a lot of this doesn't even look like French or just random symbols, just stuff that the model picked up on. So, and we have Chinese. So we can see that there's other text in this model that isn't just French, right? So it's not a perfect tokenizer. Maybe using less tokens would have been better. or maybe putting a counter on the frequency. But either way, it just gives us an idea. But here's all of our tokens, right? So there we go. Now that we have our tokens, we can actually go ahead and do this. So we're going to comment our training, because we don't need to do this anymore. We're going to do tokenizer is equal to French tokenizer. And the path to vocab will be trained tokenizer French WP .json, right? So it's just going to point to that. So we're going to do self dot path to vocab is equal to path to vocab. We have self dot tokenizer is equal to the self dot prepare tokenizer, right? So we're going to write this function now, def prepare tokenizer self, and we're going to do here our tokenizer is going to be our tokenizer dot from file, and we're going to do self dot path to vocab, right? So we're going to load our tokenizer from file, and again, this tokenizer has all the information. It knows that this is the processing NFC in lowercase. This is our pre-tokenizer. We want a word piece. It has all this information, and it's built right in. And so when we do tokenizer.fromFile, it can load all these settings in as well. So it does it for us, and we don't have to think about it. What we do need to provide is a tokenizer.decoder, right? So the tokenizer takes text and converts it to tokens, but we also need to go from tokens back to text, right? When we want to, figure out what the model generated. So in this case, we're going to do decoders.wordpiece, right? So if we trained, or if we tokenized with a word piece tokenizer, then we would need to decode as well with a word piece tokenizer. And now we can return our tokenizer, and we are good to go, right? So there we go. That will give us our tokenizer. Next up, we have our self.vocab size. This is going to be the length of self.tokenizer.get vocab, right? So there we go. Basically, how get vocab gives a list of all the words in our tokenizer. The length of that will tell me what our vocab size is. So that should be 32,000. Okay. And now we're going to store some extra information here. This will just come in handy later. So we're going to do special tokens dict. And this is going to be, just like before, unc. So it's going to be unc. And then it's going to be our pad. And then it's going to be our beginning of sentence, and then it's going to be our end of sentence, right? So there we go. And these are dictionaries, so we're going to add in our colons. There we go. And we just need the index for unc. So we can actually go look in our French, tokenizer and see that unc is 0, pad is 1, boss is 2, EOS is 3. So we can put that in here, or we can make it a little bit more dynamic. We can do self.tokenizer.token2id, and in here we can provide it that this is the unc. So token2id will take in a token and tell us what is its corresponding ID, and we're just going to pass that into all of this. So similarly, this will be the pad, this will be our beginning of sentence, and this will be our end of sentence. So there we go. Print self.special tokens dict, and there we go. That is our special tokens. Nice. Next up, we have our post processor, self.post processor. So when we are converting our text to tokens, we want to make sure that, so our text is going to have some tokens, right? Whatever comes out of it. But we want to make sure we prepend to our text a beginning of speech and append to our text an end of speech, right? I keep saying speech, but sentence, right? Beginning of sentence, end of sentence. So we want to prepend and append this BOS and EOS token. We could do it manually, or we can use something called the template processing, which is built in. So we have single, okay, so a tokenizer can actually take two types of inputs. We can either give it one sentence or we can give it two sentences. So an example of one sentence is what we're doing now. We're just going to pass it French and we want it to tokenize it, and that's it. Nothing else is happening. On the other hand, later we're going to be doing something called extractive Q&A. So extractive Q&A, you provided some text and you provided a question about the text. So in that case, we would have a double, like, or I forgot what it's called. It's something, it's not single though. Basically, we'd have two different inputs, both the text and the question about that text. But in this case, we just have the text. So we are doing single, and we're going to start it with BOS. We're going to do $A, which is the indicator for single. So all the tokens that are basically A is our sentence. A is our text. A is the actual text that we're working with. And then we can do EOS, end of sentence. So we just want to take A and prepend it with BOS and append it with EOS, right? So beginning sentence, end of sentence. And we just have to let it know that special tokens is equal to, we're going to give it a list of two things. The first one is the, again, BOS, and this is going to be self.specialTokensDict, and we can index it for BOS, and this shouldn't be a colon, this should be a comma. So that's our BOS, and then similarly, we will have our EOS, right? Just like that. So there we go. This is just a simple post processor that we're going to apply to our text that's just going to prepend and append our BOS and EOS tokens. Good. So now that we have that, we just have one last thing. We can do self.truncate is equal to truncate. Like, do we want to truncate? And we're going to do if self.truncate. Then we're going to do self.maxlen is equal to maxlen minus self.postprocessor.num special tokens to add. So the problem is, and let's see what I put here, max length. Okay. The problem is, let's say my max length is 512, right? So my model can handle up to 512 tokens. But I have a BOS and an EOS as well. So really, my model can handle 510 tokens plus these two extra special tokens, which gets it to 512. So we just need to make sure we subtract, and we just need to add here an is pair equals false. The reason it's is pair is because this is a single sentence, or we're just passing in one sample. If we're doing the double sample, like we have a question and some text that we're asking questions about, then is pair would be true, and this would be slightly different. But in our case, this is just a single, so is pair is false. So there we go. That sets up our tokenizer. So we have a couple of helper functions for that right now. Let's do def encode self input pass. So this is our function to encode text, and then def encode, or sorry, decode self input, and then skip special tokens equals true. And we'll talk about what that is in a second. But for now, let's create some fake text, which I have right here. So let's say this is my text, right? Hello world, but I put a little apostrophe on the E. So we can do toke.encode sentence, right? So that'll show us. And so if we go here and print input, we should see our input, right? Hello world. So we're going to go ahead and tokenize this. So step one, we're going to do if is instance, right? So if our input is a string, then we can go ahead and do tokenized is equal to self.tokenizer.encode input, and we can print tokenized. Right, so there we go. Now, if we look at tokenized.ids, which will give us our what the tokens are, these are the tokens that the model has decided for this text, right? So there we go. This token is decided for this text. So these are our tokens. If you take a quick look at our IDs though, notice that there's no BOS, EOS, right? There was nothing prepended and appended. So we need to actually process this. I'm gonna write another function here. I'm gonna call this process text, or let's call this tokens. And in this process tokens function, all we're going to do is just write a couple things. So first we're going to pass in here our tokenized data, right? So that's basically this. We're going to pass it in, and we're going to do if self.truncate. So if we're truncating our data, we're going to do tokenized.truncate. So luckily for us, this tokenized class, this method, this encoding class here, has a bunch of methods built in, one of them being truncation. So we can just use the truncate function by default, or we could have just done it ourselves, right? This isn't a very hard thing to implement. So maxlen, and then direction equals right? So we want to truncate, and if we have extra tokens, we want to delete from the right side of the text because we read from left to right. So there we go. And we're going to do tokenized is equal to self.postprocessor.process tokenized. So this will actually apply this post-processing to our tokenization, and we can return tokenized.IDs, because in the end, all we really care about is our token IDs. So here we can now run tokenized is equal to we can do process tokens tokenized. And there's all of our tokens. Everything in the middle is the same as before, but we've added a beginning of sentence, end of sentence tokens to it. Good. So that solves one problem. What about if we have multiple sentences? Like if we wanted to encode multiple sentences. So we can do sentence. So if we pass it in as a list, then this will not work. So is_instance string will not actually trigger anything. So we can do if is_instance input list. If it's a list, then we can do, first of all, input. We can do tokenized is equal to self.tokenizer.batch encode. So there's a nice function already built in, or actually it's encode batch. Nice function built right in that will do it for us. We want to do the input. So this will tokenize every sample independently, on its own. And then we just need to loop through. Tokenize is equal to process tokens t for t in tokenize. So we're going to use list compression, loop through, create a list of lists that will give us our prepped tokens with the EOS, BOS already prepended, ready to go. And so this will return a list. This will just return, or I guess this will return a list too, a list of tokens. This will return a list of tokens, right? So a nested list. And we can then return tokenized. So there we go. Similarly, for the decode, we need to do if is_instance input list. So only if it's a list. So let's go ahead and do this. We're going to do encode is this. Print enc. Let's pass here for now. So you can see here are my two lists of text of their corresponding tokens. So now it's time to decode them. So first of all, I expect a list is being passed in, but the question is it a list of lists or just a single list with the tokens, like the integers? So we can do if all is instance, right? So if instance item list for item in input. So if everything, basically if every element of a list is another list, that means we have a nested thing. So we can do decoded is equal to self.tokenizer.decode batch. And then we can provide it our input from before, the tokenized input. And then skip special tokens equals skip special tokens. And we can see what that looks like in just a bit. But basically when we decode our text back to English rather than, or whatever language we tokenize, whenever we decode our text back to the language, we don't really care about these EOS, BOS tokens, right? We don't need any of that. So we can actually tell it to just skip any special tokens because we don't need them. So there we go. Elif all is instance item, this would be an int. So if it's a list of integers for item in input, then we're going to do decoded is equal to self.tokenizer.decode input. Skip special tokens equals skip special tokens. And there we go, right? That gives us everything. And we can then go ahead and return decoded. Right, so there we go. You could write some exception handling in here, but I'm going to just omit that for now for simplicity. So now we can do toke.decode enc, right? We can decode it and we can print it out. Right? It tokenized and returned back both sentences. or untokenize them, return back both. If we set it our decode, if we set this to false, then you'll notice that it also includes the BOS, EOS, BOS, EOS tokens, right? So that's why you want to avoid those. Good. So this is our tokenizer prep, and we're going to leverage this tokenizer class quite a bit now and in the future. So let's go ahead and do the next step. So next step is actually preparing our data. Now that we have a tokenizer, we can actually prepare data. Now, when it comes to preparing data, like I mentioned, I love the Hugging Face format. So I'm going to take raw data that we have in those text files and convert them to a Hugging Face dataset of English-French pairs. So stage one is getting all the data and lining them up and having English and French pairs. The second step is taking our English-French pairs and tokenizing them and saving them as tokens. We're just going to pre-tokenize our data rather than doing it on the fly just to help efficiency. And I typically like that, just to pre-tokenize all the data and just have it ready to go. So we're going to do that. So we're going to write here. We need a couple things. So we need OS. We're going to need import, or actually from. Oh, don't need that. From datasets, import. We're going to load dataset, concatenate datasets, and load from disk. Right. So those are the functions we're going to need. You may not have seen these before. So this is the Hugging Face datasets again. Load dataset is what we're going to use to load our text files, but it can actually be used to load all sorts of datasets, even including ones that are online and need to be downloaded from the Hugging Face servers. We can then also concatenate together our datasets, which we'll see why in a bit, and then we have load from disk, and you'll see why we need that as well in a bit. We're going to do from tokenizer, import our French tokenizer. Right, that's the tokenizer we just wrote. And from transformers, we're going to import auto tokenizer. So this is the auto tokenizer is where we're going to grab our BERT tokenizer from for the English portion of this. So let's go ahead and do this. We're going to do def build English to French dataset. Right, so this is just going to be text, no tokens just yet. We just need to align everything together. So this should be pretty easy. We can do path to data root. We have our path to save. We have our test proportion. Let's say we're going to keep 0.5% of our data for testing validation, and you'll see why. There's a lot of data in this data set. I think there's like 40 million English French samples. We don't really care about cache stir right now, so I'm going to omit that. So that's fine. So we're going to do HF dataset is going to be an empty list. What I'm going to do, basically, is I'm going to loop through each one of these folders. I'm going to grab in each folder the English file and the French file. And then I'm going to create a Hugging Face dataset out of it and then store it in here. And then I'm going to concatenate them all together and then save the dataset. That's the goal. So let's go ahead and do that. We're going to do for dir in os.list dir path to data root, and we want to run this. It should be build. We're going to run this on path to data root. Right, so we're going to do this on path to data root. This will loop through each one of these directories, so we need the path to them. So we're going to do path to dir is os.path.join between path to data root and dir, and then we're going to do our if os.path.isdir. This is just a sanity check, right? Make sure it's an actual directory. Path to dir. As long as it's a directory, then we can do print processing dir. So that'll tell us this is the file we're currently processing, and we're going to set French text and is equal to English text equals none. We're going to set these to none for now, because we're going to make sure, in this case, I know that I have a French and English folder in each file, but it's good to always have some kind of error handling. So we're going to make sure that we have both an English and a French text file inside each folder. So we're going to do for text in os.listdir path to dir. If text.ends with, right, if it ends with .fr, that's a French file, So then we can do French text is equal to os.path.join between our path to dir and our text. Elif, right? If the text dot ends with dot English, right? Just like that. Then we do English text is equal to os.path.join path to dir, and again, text, right? So there you go. And now we're just going to do our sanity check. If French text is not none and English text is not none. So as long as we have identified a French and English text that we want to do, we can do French dataset is equal to load dataset. And so like I mentioned, the load dataset, it can do all sorts of stuff. It can load online files and it can download stuff, and it's really convenient. But it can also work with local files like CSVs, text files, Parquet, web dataset, you name it, it probably supports it. We're doing text, so we just need to let it know that this is currently a text file, right? A text file. And we need to provide it data files is equal to French text, just like that. And so if we print the French dataset, so you see what this looks like. I'm gonna throw a break in there and throw a break right there. There we go. Oh, not Tokenizer. Now we're running prepare data. Okay, so it looks like I'm missing a positional argument. We want a path to save raw. I call this raw because this is where we're going to store the raw text data, and then this is where we're going to store its tokenized version. So we're going to save two different data sets, basically copies of the same thing. So here we go. Dataset text does not exist on the hub because this should be text. There we go. That's how we tell it. So there we go. We have our data set, right? So this is saying that this is the French file that we are currently processing. Oh, and we want to look at the French data set, not the text. So now you can see that this is a data set with 320, or I guess 3,244,152 samples. So this is about 3.2 million samples of French. And we also have 3.2 million samples of corresponding English, right, that we need to load in. So let's go ahead and do that. So English dataset will load exactly the same way. So this is going to be English dataset, and we're going to load the English text, right? But everything else is the same. There we go, right? Same number, same everything. It's just English now instead. But notice actually this is a dataset dict. So it's a dictionary of train and nothing else. So you don't really need it as a dataset dict. We can just index it for train. So we're going to index this one for, we're going to index both of them for train. Oh. There we go. And train. So we're going to grab the training dataset from both of them. Now that we have that, it is time to do the rest of it. So first of all, notice this is called just text. That's not helpful. So I'm going to convert on our English dataset. English dataset is equal to English dataset dot rename column. And we're going to rename our text column to English source. And source because it's going to be our input, right? So it's our source text. So English source. And then our English dataset, what we're going to do is we're going to take our English dataset dot add column. We're going to add a column to this English dataset called French target, right? And we're going to copy into here French dataset text. There we go. Right, so we're just going to take our data, copy it in, and we'll be good to go. And once we have gone ahead and copied our French text, so we can actually look at this, print English. I guess this should just be dataset now, right? So print dataset. This might just take a second. That copy operation takes, just a second to actually copy things over. There we go. We have an English source, we have French target, and we have that many rows. So that's us copying the data in. And so we can go ahead and store in HF datasets. We can go ahead and store .append dataset, right? And this should be datasets, just like that. And we can loop through now and do this for all of our data. And lastly, we can do HF datasets is equal to concatenate datasets, HF datasets. So we're going to take all of the datasets, concatenate them together into one big dataset. We're going to call it HF datasets, right? Just so we can print it out and see what it looks like. We do need a train test split, right? Because we've only, we haven't done any train test splits yet. So we're going to do HF dataset is equal to HF dataset dot train test split. We're going to split on our training, split up our training testing data, and our test size is equal to test prop, or test proportion. And lastly, we're going to do HF dataset dot save to disk, and we're going to provide it the path to save. So let me see. I don't have anything in here. So yeah, we're going to go ahead and run this, and this should go ahead and do everything. So we're going to clear out. So we'll see that it's going to process the common crawl first. This one shouldn't take too long. It's the, I can't remember which one, but one of these takes a little bit of time. I think it's the Giga French. So yeah, we'll just give, yeah, so there you go. Giga French is happening. We're gonna let this run in the background. And while it's running, we can work on the next step. So this is to take our data and create the data set like we saw. Basically, you can imagine this Hugging Face CSV is 2 columns of data, one column having English and one column having its corresponding French. But this is just text on its own, right? It'd be better for us to have these already pre-tokenized and ready to go. So that's what we're going to do now. We're going to do def tokenize English to French dataset. We're going to do path to HF data. So this is going to, we're going to load in this. So we're saving the data set here. That's the data set we want to load. Right. So that's what we're going to do. That's what we're going to do there. We're going to give it the path to save. That's where we're going to save our tokenized data. We need our num workers. I'm going to set that to 32. So how many CPU workers do you want to use to do some of the map processing that I'm going to explain in a bit? Truncate equals true. Do we want to truncate our data? Max length equals 512. What's the maximum size that we're willing to have? And I'm also going to set a min length equals GTH equals 5. Right, so there we go. So what we need to do is load this data, tokenize it, and then save it here. And how we do that is pretty straightforward using some of these Hugging Face conveniences. As you can see here, the data set is ready. It's going ahead and saving the shards. So you can see it actually saves these data sets in a pi arrow format. Makes our life really simple. Data loading and stuff is really quick. And the data is already pre-sharded. So instead of having one giant file with all of your data, it's going to split it up into kind of 30 smaller files, so on and so forth. So that gives us everything we need there while that's running, right? So we can do our first, our tokenizer, right? So we have French tokenizer is going to be our French tokenizer. And we're going to do the path to vocab is our trained tokenizer and then French word piece.json, right? So there we go. That's our French tokenizer. And I believe there was some other information. Truncate equals truncate and max length equals max length. That's our French tokenizer. Our English tokenizer, similarly, will be loaded by the auto tokenizer. So this is one of the auto classes built right into Hugging Face, where basically I can do auto tokenizer.pretrained and just pass into it my name of the model of which tokenizer I want. So I can do Google BERT, BERT base uncased. The base and stuff don't matter. I think all the BERT models use the same tokenizer. The important part is uncased. We are using, this is all lowercase, and which is why we also made our tokenizer lowercase, just so everything's lowercase and it's the same and convenient. So there we go. So we have our Google BERT base uncased, which we'll be using for the English portion. And our raw data set is going to be load from disk, our path to HF data, right? So that's the data we're going to load. We can print raw data set just to make sure it works correctly. Okay, so we'll come back to that in a second when that's done. Right, so step one is we need to tokenize our text. So to tokenize, how we can do this is we can either A, for loop through every single row in our data set and tokenize it. But as you can see, there's about 40.6, 40.7 million rows in this data set, and that would take a while. So instead, can we do multiprocessing and prepare our data in batches, right? That's the main idea. Well, we actually can, right? So the Hugging Face, again, why I like using the Hugging Face dataset stuff is because a lot of this map processing over an arrow dataset is already automated and super easy to use. All we need to do is provide a function that we want to apply. So this is done. So let's go ahead and print the raw dataset. Print raw dataset. And instead of building the dataset now, we want to do tokenize. We're going to run this function. And it's going to be between path to save raw and path to save tokenize, right? That's where we're going to save it. And just to give an idea, it created this folder called HF all data. Inside you have kind of train test splits, and here are all those arrow files where that data is saved and that sort of stuff. So we have everything. Now that we have this ready to go, we can actually run this. Oh. Let's clear this out. There we go. And you can see it loads it. We have about 203,000 samples for validation, about 40 million samples for our training. So we have everything we need here. How do we access some of this data? So we can actually index. So you can see there's a train split and test split. Let's look at the train split, and let's just look at the first sample. So we're going to do 0, and you should see basically a pair. We have our English source, notably has been indubitably established that yada yada yada, and then we have its corresponding French as a dictionary. Now, what happens if you index multiple things? Like if we index 3 things? Well, in Hugging Face, these data sets, it basically concatenates. So it'll give you a list of the first 3 English things in the English source, and then the first 3 French things in the French source, right? So it just concatenates them together. So we're going to leverage this in our processing. So we're going to do def tokenize text is the function we're going to write, and we're going to pass in examples. And examples will basically just be a list of examples. So it'll look basically exactly like this. It's going to be a list in the English source and a list in the French target. So we're going to do exactly that. We're going to do English text is going to be our examples. And we're going to pass in here English source. And then our French text is going to be examples. And in here, we're going to pass in the French target, right? So we're grabbing the English source for our list of English, and we have our French target for our list of French. So there we go. And we're going to go ahead and tokenize them. So this is why in our French tokenizer function here, we spent a little bit extra time creating these functions to deal with lists, right? So to process a list of text rather than just a string. That's the main reason, just to make some of this stuff a little bit cleaner. So now that we have that, we can do source IDs is going to be our English tokenizer, and we want to apply it to the English text. We also want to make sure truncation is true, so truncation is truncation, and max length equals max length. And this will return, as you can see, source IDs. And let's raise an exception so it breaks here. And to apply this function, how do we actually use this function instead of for looping through all of our data? We can do tokenized dataset is equal to raw dataset dot map, and we're going to map this tokenized function, tokenized text function. And we're going to say batch equals true because I want this to train in not train, but I want it to be tokenized in batches. So every CPU core, there's 32 of them. Each of them will be processing a batch at a time. So batched is true. I'm going to also set the batch size to 2 for now, just to make this point clear. Otherwise, it'll just be a big wall of text and we won't be able to tell what's going on. So let's go ahead and run this. As you can see, it returns input IDs. These are my tokenized text, right? And then we also have some token types and attention mask and some of this other stuff. We are going to ignore this right now, this token type, attention mask. We're going to be building our own attention mask a little bit later. We're not going to be using this one. So all we need is input IDs from here. So we're going to go ahead, take this and convert it to input IDs, just like that. That's our source text. And then we have our target IDs, right? So target IDs. This is going to be our French tokenizer that we wrote. And this one returns the input IDs by default, so we don't have to worry about it. But yes, it's going to be our French tokenizer. And we are going to do .encode French text, just like that. And this will again return exactly the same. So we can return this as batch is equal to source IDs, and this is going to be our source IDs, and then our target IDs is going to be the target IDs. And we can go ahead and return the batch. Now, the reason for me to convert this to a dictionary is because how the Huggingface dataset and the map stuff works is any key that's here that's not in the that's not in the dataset. So basically, we don't have a source IDs and target IDs column in our dataset right now, right? We just have English source and French target. So it's going to add 2 new columns called source IDs and target IDs to our dataset. So now our dataset will have a total of 4 columns in the data. The original English and French, and then the tokenized English and French. And our tokenized data will already have some of those, we'll have the end of, the beginning of sentence, end of sentence, all that stuff already added on. So this is going to go ahead and do that. I'm going to let it do for the default batch size. I'm going to add num proc equals num worker, so it better utilizes my system. After we've tokenized the data, we can go ahead and actually tokenized dataset is equal to tokenized dataset. We can actually do .remove columns. We don't actually need the English source anymore, and we don't need the French target either. We don't need the English or the French because we've already tokenized them. So the original text is no longer important to us. We already have the tokens. That's why I create 2 datasets, one that had the text, and the second one will be one that just has our token. So I'm going to go ahead and just delete these 2 extra columns. Once we have that, we need to now filter for the last thing. We want to make sure any French text that's shorter than 5 words could cause some problems, like there's just not enough text there, or 5 tokens. So we're just going to go ahead and clip it so it's like a reasonable length sample, right? So we're going to do that. So we're going to do tokenized dataset. Actually, we're going to call a filter func. We're going to create a function. And to do this, there's a bunch of ways we can do it. I'm just going to create a lambda function that's going to take in a batch or examples, right? Just to keep it the same as before, examples. And what it's going to do is we're going to loop through examples. We're going to do, for each sample, we're going to compute the E. So we're going to len E for E in examples target IDs. So we're going to loop through all the target IDs. Remember, example target IDs will return a list of lists, right? So we want to compute for each of the lists inside our examples, what is the length? And if it's greater than the min length, right? Just like that, GTH. Lambda, no, this doesn't need a colon right here. There we go. Lambda examples, and there we go. So again, we're going to check. This is going to return a Boolean for every sample. Is it greater or is it less? And our filter function, so the Huggingface filter function by default, will only keep the samples where this condition is met. If it's not met, then it won't be kept. So there we go. And we're going to do tokenized data is equal to tokenized dataset dot filter, and we're going to just pass in our filter func. Right, there we go. And we can finally print our tokenized dataset just to get an idea of what that looks like. And lastly, we need to save our data. So we're going to do tokenize dataset dot save to disk. I'm going to save to this to the path to save. Right, that's where we're going to save it. So I'm going to save it in a folder called HF tokenized. So let's go ahead and run this. This is going to take a second. I can also maybe, actually it's fine for now. Let's just give this a try and see what happens. See if there's any bugs. No, it looks like it's working. So it's going to take about 3 minutes to tokenize all of this text. So not too bad. For 40 million samples, 3 minutes is a completely reasonable amount of time to wait. If we tried to do a for loop, this would take considerably longer than just 3 minutes. And as you can see, it's iterating in groups of 1,000. By default, the batch size set in all these functions is 1,000. That's just how the Hugging Face thing is set up, a batch of 1,000. It's going to go ahead. It's going to save our data set. And now we have everything we need to work on our data loader. So I'm going to go ahead. So this is going to take a minute. So I'm just going to let it run. And if it takes too long, then I can go ahead and cut the video a little bit, but that's fine. But we need a little bit of work. So while this is running, let's actually draw out what we're planning on doing. What does our model structure look like? So what we're going to have is we have basically English-French pairs, right? So let's draw this in here. So let's say we have English, right? This is our English. And there's going to be some word one, whereas let's actually use let's use English E1, E2, E3, E4, E5. So we have our English tokens, and we have its corresponding French, right? Corresponding French, and that'll be French 1, French 2, French 3, and let's say this French 4, right? Because these don't necessarily have to be the same length, right? Which is why we like sequence-to-sequence models, and we'll get into more details later. So this is going to go to a transformer encoder, right? Encoder. And this is bidirectional. So this should look a lot like that. Basically, what we talked about last time, a bidirectional encoder can look both directions. So when we're computing how words are related to each other, we can look at both passwords and future words, right? So passwords and future words. So if we're trying to understand something about the E3, the third English word, it can look to the passwords like English 1 and English 2, but it can also look to future words, E4 and E5. And this is going to produce some vector or some matrix that looks like this, right? It's going to be sequence length, which in our case is 5. So we're going to say S equals 5. There's 5 words here, and embedding dimension. And each of these tokens in our matrix represents how this word was related to all the other words. So again, if you're a little bit confused about this, just take a look at the previous video on attention. We still haven't talked about transformers yet. We'll be building that in the next video. But again, the bulk of the transformer is the attention mechanism. So just to, imagine that. This is our attention, output of attention. So we have that sequence by embedding. The French, on the other hand, is, okay, so this is encoder, so it's bidirectional. The French, on the other hand, 2 things are going to happen. First, we're going to add a beginning of speech token, and then we'll have F1, F2, F3, F4, and then we're going to have our end of speech. I keep saying speech, end of sentence token. Right, so there we go. That's our setup. So we have 4, and we just add these extra 2 tokens on the end. And then this is going to go to a transformer decoder. Right, so this is a causal model, and this will look a lot like the LSTM for generation, right, where we use every single where a word can only look at passwords. So this means F1 can only look at our beginning of speech token. F2 can only look at beginning of speech in F1. F3 can only look at beginning of speech F1, F2, ... right? We just continue on this pattern. And to do this, we use that causal mask that we talked about, right? The causal mask. I'm not going to go too much into the architecture just yet. We're going to leave that for next time. But I do want to talk about how the data was set up. So how did we do the generative task for the Harry Potter? Well, we had a model, if you remember. We had like word 1, word 2, word 3, word 4, let's say. These all went to some hidden state, right? We learned something about them, went to some hidden state. And this is for the RNN, right? And these hidden states were connected to each other via the RNN mechanism. And then at word 1, our causal task is next token prediction. So given word 1, I want to predict the next word. What's the next word? The next word's word 2. Given word 2, I want to predict the next word. So actually, given word 2 and word 1, I want to predict the next word. That's going to be word 3. And then given word 1, word 2, and word 3, I want to predict the next word. That's going to be word 4. And then given word 4, we're going to predict word 5, ... So if you remember, we basically did a offset alignment of our data. So if we have the text word 1, word 2, word 3, word 4, and word 5, our input was going to be word 1, word 2, word 3, word 4. And our output is going to be word 2, word 3, word 4, word 5. Right? So we basically offset them by 1. And as you can see, right? So word 1 predicts the next word, word 2 predicts the next word, word 3 predicts the next word, ... Right? We just predict the next word over and over again. So transformers are no different. So this means our input is going to be our beginning of speech. This is super important. We'll see why later. Then we're going to have F1, F2, F3, F4. And then our output is going to be F1, F2, F3, F4, end of sentence. Right? There we go. Now that we have this, just again, the important part is when we're generating, right? So also remember, we had that cross attention. Don't think too much about the architecture right now. This is just to kind of give you an idea of the data. But our cross attention is going to be, as we're generating, we also want to understand how is our French related to our English, right? That portion will happen as well in the transformer. But you can imagine that basically, given the English context from our transformer encoder, and the beginning of sentence token, I want to predict what the very first word of our translation is. And then given the beginning of sentence, the first word, and the English context, I want to predict the first 2 words, the second word, right? Our second word. That'll predict this. And then again, given the English context and the first 2 words, I want to predict the third word. And then ... we continue. But at some point, like F4 will predict end of sentence. Once our model predicts end of sentence, we go ahead and stop generating. So the model has to decide, when do we stop generating? Otherwise, it'll just keep writing, right? It can write for as long as it wants. It'll just keep generating 1 token at a time over and over and over again, and it'll just keep going. So this way, the model has to identify, when am I done translating? Like when have I translated correctly? Everything has been said. So that's what the end of sentence token will be used for. But the key idea is there's basically 2 data sets going on. We have our English data right here. We have our French data. And for the French data, we need to offset it like this, right? Basically, everything except for the last token for the input, and then everything but the first token for the output. So we need to offset it like this. For the English data just stays alone, right? We just pass the whole sentence in, and that's done. There's one last piece as well, our padding tokens, right? So padding. For padding, we have a whole section, or I have a whole section going in depth into padding in the last video. So again, please just go check that out where I talk about it. But in padding, we're going to have padding. We're going to have English padding, right? Because every English sample, remember, we're going to train in batches. So we have to pass a batch of English and a batch of corresponding French. Every English sample is going to have a different length, because different sentences have different lengths. So that means we need a padding token here. And similarly, every French sample is going to have a different length, because every French sentence has a different number of tokens. So we're going to have to also have French padding. So we're going to have 2 pad tokens, pad masks, one for English, one for French. This is going to be known as the source pad mask or something like that. And then this is going to be known as the target pad mask. And we're going to need both of these in the future, right? We're going to need all of this. So let's check on our data, see how that's going. looks like there's a mistake here. Examples, target IDs. Let's see here. In our filter function, what am I missing? Let's see here. Actually, yes. Okay. We need to set here batched equals true. Okay, basically, and this is how the Huggingface dataset stuff works. If you notice here, this is actually a good thing that this broke. The object of type int has no len. Basically, when batched is not true, the input to our lambda is a single example that isn't in a list. It's just a single example. So basically, at this point, it was doing len of the tokens themselves, like the integer tokens. That's not helpful, right? We don't want that. This only works if it's a list of lists, right? So a list, and inside each list, we have a list of the tokens that go with that. So that's why when we do batched equals true, then we actually get the list of lists. So we can go ahead and do that. The other cool thing about Huggingface datasets is this. So when you run this, notice that it jumps straight to filter. It actually did not run this tokenized text, this function again. It's because it already hashed and saved this function, and it has been cached inside your Hugging Face cache directory. Now, one thing to keep in mind when working with big data sets, that cache directory can start to get really big and use up a ton of disk space. So this is why I typically like to do all of my processing on my data, get everything exactly how I want it to be, and then just go ahead and save it rather than depending on the cache directory. But the cache directory is quite nice when it comes to factors like this, methods like this. So now that we have everything, we're going to let this keep running. I bet we can write a bit of this before. I think we should be good to write this. We'll run it when this is done running. Hopefully there's no bug again. So this time we're going to write a new file called data.py. So in here, we are basically going to define our collate function. So we've talked briefly about collate functions in my original dataset data loader video. This is just going to be that, just more complicated. So our input is going to be French and English token IDs, like a batch of them, right? So we're going to have basically a bunch of, let's say English, right? So we're going to have English. Wow, I can't write today. English, and we're going to have some samples, and the first sample might have like 5 tokens, right? And the second sample might have 3 tokens, and the third sample might have 4 tokens, right? Let's just say that, right? So that's what they are. And similarly, we'll have French, right? And these will be the corresponding tokenized French tokens. Like we might have 6 here, and then we might have 4 here, and then we might have like 2 here, right? So there we go. So we have our corresponding French tokens. So step 1 is we need to go ahead and pad it, right? We need to pad it. So again, if this is the longest thing, we need to pad the shorter sequences to the longest one with our pad token. And we're going to have 2 different pad tokens because we have an English tokenizer, which means our English tokenizer has its own pad token. And then we have a French tokenizer, and that French tokenizer has its own pad token. So we're going to go ahead and just pad our data to the shortest or to the longest sample in both of them. We also need to produce, like I mentioned, the padding mask, right? The padding mask. And that'll be pretty easy for us to generate once we have our pad token. Let's just let that keep running. I think it'll be done by the time we get closer. So let's do import pandas as PD. Actually, do we need pandas for anything? Why do I have pandas here? I should get rid of that. We don't need that import. Okay, I'll clean that up later. No problem. We need import torch. We need import torch.utils.data. Actually, not import. We need from torch.utils.data import data loader. So a really neat part about Hugging Face datasets is before, right? Before we'd have to write class, data, dataset, and then we do like a def init, and then we do a def len,
And then we'd have to do a def get item, right? We've done this before, right? We've get item, right? We've done all this before. We've written a data set and then we load this data set into our data loader, right? We've been doing this over and over again. We write a data set and then in that data set's the logic to grab one sample at a time, and then we give that data set to the data loader. We can actually just directly give the Hugging Face dataset to the data loader. So it interfaces perfectly with it, which is great for us. So we'll be giving that, but we need to write the collate function. And if you don't remember, the collate function is, again, we have samples of different lengths. We just need to, how do we stick them together? In images, it's easy. You just resize them, put them together, you're done. In text, we have all this padding stuff like I just talked about. You're almost done, so we're going to let that keep going. We're going to need from tokenizer, import French tokenizer. We need from transformers, import auto tokenizer. And we're going to need from model, import, why do I have my transformer config in here? Let me just double check. Don't need that import either. I guess I was just debugging stuff when I was going, so we can ignore that. We're going to do from datasets, import load from disk. And we're going to need that to kind of verify what we're working on is actually correct. So there we go. We're now going to do def translation collator. So I typically like doing collate functions as like I have a input. So source tokenizer, target tokenizer. And this is just going to be a wrapper on our collate function. So almost every collate function I'll be writing in future videos. Typically the collate function has some input. So I think by default, the collate function, you can only pass in the batch like this. I'm sure you can pass in kwargs or something like that, but I'm going to keep this simple. So this function has this collate function in it, and this function is going to return the collate function back. And that's the easiest way I found to do it. That's the most readable, so we're going to do that. Here we go. Dataset's ready. It's just going ahead and saving. But as you can see, nothing changed. The number's gone down a little bit because we deleted all the samples that are less than 5. But other than that, we're good to go. We're going to do target IDs is equal to torch.tensor I source IDs for ID in batch. So again, basically, or I in batch. So we're going to, again, this batch will be a dictionary, or sorry, a list of stuff, right? It's going to be just a list of stuff. So we just need to loop through that list and convert each thing in that list called source IDs into a tensor. And the thing is, each of these tensors, each of these source IDs, right, could be of different lengths. Like we have one that's 5, one that's 3, one that's 4. But that's what this is. It's just a list of tensors, and each of these tensors are our source IDs. That's all. Similarly, we're going to, actually, this should be source IDs then, SRC. Similarly, we need a target IDs. Again, torch.tensor I. This is going to be target IDs for I in batch, right? So again, we're going to loop through our batch for I in batch, and we're going to index out the target IDs. So the way this data will look is going to be a list of source IDs, and then it's going to give a list of stuff, right? Those IDs. And then it's going to be a target IDs. And it's going to be a list of stuff. And because we are training in batches, right, there's going to be a list of lists. So we're going to have many of these. Source ID, target ID, source ID, target ID, so on and so forth. So that's everything. And so what we're doing is looping through the list for I in batch, and then grabbing either the source ID or the target ID, corresponding one. So that's what this batch is going to be by default. Right? And it's our job to stick it all together. So first of all, source pad token, we can actually get this by doing source tokenizer dot pad, or source tokenizer dot pad token ID. So basically the Roberta or the BERT tokenizer, and I think basically every tokenizer that Huggingface has the attribute dot pad token ID. It'll tell you which token is our pad token ID. Because when we do our padding here, right, when we pad the shorter stuff to the longer stuff, we want to make sure we're using the pad token ID to do that operation. So there we go, pad token ID. We're now going to do source padded. This should look familiar. We've done this before. torch.nn.utils.rnn.pad sequence. Long function, but basically we're going to pad a sequence. To the pad sequence function, you pass it a list of tensors that are of different sizes in our case. So we're going to do source IDs. And you provide it batch first is true, because I just like it that way. So it'll be batch by sequence by embedding dim, or in this case, just batch by sequence. So we're going to do batch first is true. And then we have to provide it the padding value. Like, what number do we want to pad with? Padding value will be the source pad token. So simple as that. Our target will be the same. So we can do target pad token is going to be target tokenizer dot special tokens dict, right? Special tokens dict. And we're going to just index out our pad token. This is why in the tokenizer, we created this special tokens dict that tells us the pad token and its corresponding number that goes with it. We used it because we created it so we could use it right here. So we have our special tokens dictionary, and we're grabbing the pad token. Great, so that's our target pad token, and everything else is the same, right? So we're going to do, not quit, target IDs, or sorry, target padded is going to be target or torch.nn.utils.rnn.pad sequence source, or in this case target IDs, again batch first equals true, and we're going to do padding value is going to be the target pad token. So that sets everything up. That is our padded data ready to go. There is one step, so this looks like it's done downloading. So let's actually go ahead and load it. So we're going to do if main equals main. We're going to do path to data is going to be, and we can actually copy this path. Let's grab it from here. Long paths, but that's okay. And our data set is going to be load from disk path to data. So we can print out our data set, take a quick look at it, but it should look fine. Nope, I don't want to prepare data again. That's my bad. Python data.py. We're running wrong file. So there we go. It's going to load the data from disk, and there you go. There's our data. Right, so no problems there. Source IDs, target IDs. We can look at one of the samples. Let's look at train 0. Right, so here's the source IDs for one sample and the target IDs for one sample. So that's good. After that, what we want to do is we can actually do loader is equal to data loader, and we can just directly pass in the data set. And I'm going to give it a batch size of 2, let's say, for now. And so now that we have that, we can try to run it. We can do for samples in loader print samples and break, right? And what we should see is a bug, right? Actually, first of all, we need to give a data set, not just data set, but if you remember, there's a train and test split. So we need to give it like the train split. So we're going to do data set bracket train, just like that. Okay, let's try that again. So there we go. Each element in the list should be of equal size, right? So it can't concatenate stuff together as expected. So we need to use our collate function. So let's go ahead and use it. So we're going to do our target tokenizer is going to be our French tokenizer, trained tokenizer, and then French word piece. Wordpiece.json. Right, so there's our French tokenizer. And then we have our source tokenizer. It's going to be auto tokenizer.French from pre-trained Google BERT, and it's going to be the BERT base uncased. So there we go. There's our tokenizers. So now we can define our collate function. The collate function will look like this. Collate function is the translation collator, and the translation collator needed the source tokenizer and the target tokenizer. So that's everything we need. And then we can pass to our data loader our collate function, right? Just like that. So we've seen this before when we're doing the RNN stuff, but that's all it is. And so now we can look at our print source padded, right? Let's see what this looks like. We should see, it looks like print source padded actually didn't print anything out. Oh, of course, because return collate function, right? We have to actually return the function. So this translate collator returns a function which goes here, and then I pass this function to there. So there we go. So there we go. That's our tensor. There's the first ones. There's the second ones. And it looks like the pad token is 0 for the BERT based on case. So anything is 0 for us too. So there's the padding occurring, right? We're padding our tensors. Similarly, the target padded, right? We can print that out because that's an actual tokenizer that we wrote. There we go. Oh, it looks like I think the pad token, we can actually check. Our pad token is 1 in our case. So different tokenizers, different ways. And it's okay because we're going to have 2 different embedding matrices too, right? One for English, one for French. So it doesn't matter all that much. But you can see we concatenated some ones to do the padding. I can run it one more time. Actually, I don't think it's random, so it'll always be there. Okay, good. Good. So we have our source padded, target padded. The last thing we need is our mask, right? So we're going to do source pad mask is going to be where the source pad padded is equal to the source pad token. So it'll look something like this, right? So it's going to be true where it's where we have a pad token. It's going to be false where we don't have a pad token, or vice versa. So I think in the previous video, I had it true where there's no pad token. So true on the tokens we want to compute attention on, and false on the tokens we don't want to compute attention on. So instead of false and true, we need to flip them to be does not equal to, right? So this will make it in line with how I implemented it in the attention video previously. Obviously, you can do it however you want to. As long as you're consistent about it, then it's up to you. So we're doing true on all the non-padded tokens, things we want to compute attention on, and then false on things we want to compute attention on. Or sorry, we don't want to compute attention on. So there we go. We have our true-false mask. We're going to create the exact same mask for our target, but before we do that, we need to go ahead and create our input and output for the causal prediction. And that's coming back to this, right? We need to take all of this and do everything but the last thing as our input, and then the first thing to the end for our output, because we're basically offsetting everything by 1, so we can predict everything one at a time. Again, for the cases of the RNN, right, we use W1 to predict W2. We use W1 and W2, or W2 to predict WT, W3 to predict W4, W4 to W5. So we just need to cut and offset it, just so it's set up exactly the same way. So we can do input target is going to be our target padded, and we want all the rows in our sample, right? So that's the batch dimension, so we want all the rows, and we want everything but the last thing as our input. And we're just going to do a dot clone to create a copy of this tensor. And then our output target is going to be, again, target padded, all the rows, we want all the samples, but we want everything except for the first sample, right? Because it's offset by 1. Again, dot clone. So that's doing exactly here. In the input, everything but the last thing, and in the output, everything but the first thing. So there we go. That's us doing the offset. Again, looks very similar to what we saw in the RNN stuff a few weeks ago. or a few videos ago. And so now we can go ahead and do input target mask is going to be where our input target does not equal to the target pad token. So tell me where it's not pad token, so exactly the same as before. And this is the most important part. We're going to do output target where the output target is equal to the target pad token. We're going to set it to -100. Okay, so why did we do this? So imagine this. We have, remember the next token prediction is, okay, so it's going to look something like this. So we have word 1, word 2, word 3, and then a pad token, right? And so our next token prediction is W1 should predict W2. W2 should predict W3. W3 should predict W4. And the pad, well, what should the pad predict, right? Is kind of the question. And technically it shouldn't predict anything, right? Shouldn't predict anything. We don't care about the pad token. So we set so these are the labels, right? Labels. W1 should predict W2, W2 should predict W3, W2 should predict W4. But the pad token shouldn't predict anything, or it can predict something, but we shouldn't include it in our loss function. So we can set this to -100 because by default, the PyTorch cross entropy loss, so if we can pull that up real quick, cross entropy loss, the PyTorch cross entropy loss is going to ignore index -100. So any sample that has a label of -100 in the label, so anything with a -100 will be excluded from the loss because we don't really care what the pad token predicts, so we just want to ignore it. And so this is why we will set any pad token we have to a label of -100. So W1 will predict W2, W2 will predict W3, W3 will predict W4, but this pad token and any other future pad tokens will all be predicting -100. So when we go to compute the cross entropy loss of what is the next token in our model, then there really won't be anything to calculate there, right? We're just set it to -100 and it'll automatically filter it and ignore it for us. So there we go. We could also filter it ourselves, right? I mean, it's not that we have to do it this way, but why not leverage stuff that already exists, right? So it just makes our life easier. So our output target, right? Our output target is basically going to look like this. So in this case, there's only one sample, right? Or two samples. So there we go, -100. So that's all it is. We're just swapping things to -100 that were pad tokens. Let me print target padded real quick. Target padded. There we go. Yeah. So yeah, everything looks correct. All right. So now that we have our everything ready to go, we have our output target. We set anything that is a pad token to -100. We can just go ahead and return this batch, right? So we have all the information we need. Our batch is going to be everything that we need. So it's going to be source input IDs, right? So that's going to be our source padded, right? So there we go. Then we have our source pad mask, right? So that's our padding mask. That's going to be the source pad mask. We have our target input IDs. So that's going to be target padded. Actually, no, this is going to be input target, right? So our input to our thing. We then have our target pad mask. This is going to be our input target mask. And then lastly, we have our target outputs. And this is going to be output target. So that batches together everything we need, right? We have our padding, we have our inputs, the English inputs. We have its corresponding pad mask because we don't really care about computing attention with the pad. We have our target, right? What is the thing we want to predict? We have our target inputs, basically the input to our model. We have our outputs, the next token prediction targets, and we have also our pad mask for that. So this is all of the data we need for training. and we can return batch. So this will set us up. We can now go ahead and give this a try. So this should work now. So let's give this a try. Python data.py. And we should see a batch that looks like this, right? So we have input IDs as a tensor, but you can see there's padding, right? We have our pad mask identifying that, hey, all these zeros are not things we want to compute attention on. So false. We have our target input IDs. These are the inputs to the model. So we have 26842, 22651. And then we have its outputs, right? So 2 needs to predict 6842, so that's 6842. 6842 needs to predict 22651. Well, there's 22651. So the next token prediction. And obviously different French things, different French sentences will have different lengths. So we need to make sure we pad, we ignore our padding, right? So we ignore our padding. And again, that's right here. So this one right here is a pad token for this French sample. So we have a false here because we have no interest in computing attention on that. We can also do a shuffle equals true, right? So we'll always get different size samples for our, different samples every time we run it. So there we go. And the last thing I want to show is if we do this, num workers, let's say 32 workers. And I'm going to use a batch size of 128. And we're going to do for samples and loader. I'm going to throw a TQDM on there. I think we need to import that. From TQDM, import TQDM. And I'm just going to throw a pass here. The cool part about Huggingface datasets especially, is they are blazing fast. And here's some evidence for that. So again, remember, we have about 40 million samples in our dataset, just under, and we get to loop through it in just 5 minutes, right? So in 5 minutes, we get to loop through a ton of data. So not bad. Very fast data sets, very fast data loaders. Makes our life much simpler. So either way, this is the full preparation of the data. So as a recap again, we went ahead, we wrote a tokenizer for our model, mostly for French. Again, we could have used an existing French tokenizer online, because I'm sure Hugging Face just has a French tokenizer that we could have used. I wanted to just go through the process of making one because it sounded more fun. So we wrote a tokenizer, and all of this stuff here is just a kind of a wrapper function to make some stuff like encoding and decoding a little bit simpler for us. So there we go. Our data set, our tokenizer is ready. Once we had the tokenizer, we could then actually take all of our data, put it together, and then save it as a Hugging Face dataset. This line right here to add column actually isn't the smartest because we need to basically grab all the data from French, the French text, load it to memory, and then copy it to English. I'm sure there's a better way to do it, but it's fine. It works for now, so if it works, I'm not going to complain. And then we have to go ahead and take this data set that we made and tokenize all of it, right? Convert it to tokens. And so what we end up with is our final data set is token-to-token correspondence. We have an English column, a French column, and we have the tokens of the English and the tokens of the French. Once we have all that, we can then write our collate function, right? This is basically going to take our tokens of our English, tokens of our French, make a list of them. And the problem is every sample in our batch will have different lengths. So we need to go ahead and pad our source and then compute its attention mask. And then we need to pad our target, do the causal offsetting, and then create our input attention mask, right? The input target attention mask. So we're not computing attention in our decoder transformer on padding tokens. But we also need to make sure that any pad tokens that exist inside our output, the thing we want to predict, is set to -100 because pad tokens shouldn't predict anything. So we should ignore them in our cross entropy loss in the future. And then we can go ahead and batch it all together, just create a nice little dictionary of data and return it. And we get something like this, which wraps up everything for today. So again, in the next video, we are going to actually implement transformers and train the model. So it's going to be a much longer video where We're going to put all the pieces together. We're going to kind of gloss over attention a little bit more because I have a whole video for that in the last one. So we're going to look at attention. We're going to implement the other pieces, and then we're going to spend a lot of time writing a proper distributed training script on Accelerate to get this all going. Either way, if you have any questions, comments, concerns, just leave it in the comment section below. I will see you in the next one.